Very good. Welcome, everyone. Good morning, good afternoon, and good evening, wherever you are. So this is the last session of our workshop. Uh, and today definitely is interesting. We are going to cover comparisons of models. We are going to cover the coded version of these models already available that you don't have to code it yourself. And Steve will have a couple of real-world examples of how to use these models. And finally, Steve is going to give an overview of mm, a project about probabilistic fault displacement hazard for the state of California, which Steve is going to touch on that. Welcome again, and I pass it to Alex.
All righty. Thanks so much, Yusuf. Let me get my screen share in here. All righty. I think everyone can hopefully. Can you see the presentation? I don't see the magic green box.
Yes.
Yes, oh good. Let's get the pointer. Alrighty. So very quickly, I want to mention or remind everyone that on Wednesday, we heard a series of great presentations on some of the newer models that have been developed by the broader community, as well as the 4 new fault displacement models that were developed by the FDHI group. And these presentations covered the most important parts, the essence of the models and their implementation. But there are a lot of really interesting details about the model development that we didn't have time to cover. So I really hope you'll be able to read the papers that go with all of these models the papers are coming out very soon and in some cases are already available. So moving through the agenda, today I will give a very brief overview of how the new displacement models compare with each other and some of the earlier models that Dr. Moss mentioned on Monday. It's a very quick overview, but we have many more comparisons and presented in a much more comprehensive way in the technical report that goes with this, as well as a paper in earthquake spectra that is in review right now. And as with every other part of the FDHI project, what you see here really is the result of a collaboration with major contributions from all of the model developers in the FDHI project. So we've learned over the last couple of days that there are 4 new fault displacement models that have been developed through the FDHI project. And this table here on the right lists the members of the modeling teams of the 4 new models, as well as the abbreviations that I'll use throughout the rest of this talk for these models. So as I mentioned, I'm going to show some comparisons of these 4 new models and the 3 earlier models that a lot of you maybe are familiar with, the Young's 2003, Peterson et al. 2001, and Moss and Ross 2011. And these models all provide fault displacement probability distributions for either the principal or aggregate displacement. And we have also heard over the last couple of days that the models use different definitions of displacement. So this table here on the right summarizes the definitions that are used in each of the models. And Dr. Thompson went over this on Monday, but I want to remind everyone that 3 of the new models sum displacements across parallel ruptures. And which ruptures are involved varies based on the model. And as well, 3 of the new models predict the net component of displacement. We talked about this on Monday as well, that there are some data limitations in this net component that we should try to be cognizant of. So I won't say too much here other than to mention that this table on the right is here to remind us that these models are developed for specific styles of faulting, and they're applicable to specific magnitude ranges. And it's generally important to stick to these criteria when we use the models. So some of the key improvements over the earlier models include the use of a much larger database. We heard on Wednesday that depending on the model and the style of faulting, many of the new models use a nonlinear magnitude scaling, and we find that that gives us much better fits at the magnitude extremes, the smaller and larger magnitudes. And the aleatory variability modeling effort in these new models really is pretty sophisticated and in line with what you would expect from modern models these days. Each model uses a different non-log normal distribution. The variability is based on our location, that normalized location along the rupture length or magnitude. And most models partition the variability into between and within event components. So the new strike slip and normal models use bilinear or in the case of Lavrentiadis and Abramson, trilinear magnitude scaling. So this plot on the left shows the magnitude scaling in terms of the average displacement along the rupture for strike slip faults. The dashed black line here is the average displacement that's implied from the Peterson elliptical model. The little bit steeper straight gray line here is the Wells and Coppersmith magnitude scaling relation that you're probably familiar with, perhaps for strike slip faulting. And then the brighter colors here are the newer models from the FDHI program. And we can see that these newer models, we have steeper scaling out here at the smaller magnitudes and much flatter scaling at the larger magnitudes. I do want to mention that the new models do predict larger displacements around magnitude 7. So this is roughly near the breakpoint or the upper breakpoint in the nonlinear scaling. And interestingly, this magnitude 7 is also the richest part of the database for strike slip and normal events. So there's a good bit of data that is telling us that we're seeing larger displacements here around magnitude 7. For reverse faulting, the magnitude scaling, it approaches linear or is linear in the new models. This is the same type of plot for reverse faulting with the average displacement along the rupture on the y-axis. And the dashed black line is the magnitude scaling from the 2011 Moss and Ross paper. And we can see that again, the newer models are in the brighter colors, and the newer models have a steeper scaling compared to Moss and Ross 2011. But the Wells and Coppersmith all styles of faulting, the newer models do have flatter compared to the all styles. I do want to actually, before we move on, draw attention to maybe the fact that the 2024 Moss and Ross model, the red line, you might notice at larger magnitudes, it's quite a bit lower than the other new models, the LA and KEA. This is due to several different factors. It's a little bit complicated. It is, of course, related to the different definitions of displacement, and particularly that effect of summing the displacements across parallel ruptures. But the modeling approaches also were very different for average displacement. The Moss et al. 2024 team uses a regression of magnitude on the mean displacement for a given earthquake, just like the Wells and Coppersmith magnitude scaling relations. But the LA and KEA models, their average displacement is derived from their location-dependent fault displacement model. And it's done by essentially taking the predicted average displacement at every location and then taking the mean of that. So these different approaches to developing the average displacement regressions are one of the big drivers in the differences in the magnitude scaling for reverse events. So a fun feature of fault displacement models is that they all use different data transformations and statistical distributions. This table here on the right summarizes the data transformation for each model and the statistical distribution. You can read about these details in the papers and the reports, but the important thing to note is that they're all different. And so that means if we want to compare the aleatory variability, we can't just pick our favorite statistical distribution parameter like the sigma or the standard deviation and make meaningful comparisons. The units might be different of the parameters, or it might just not be a meaningful unit for that distribution, meaningful parameter for that distribution. So instead, the best way to look at the aleatory variability is to look at the probability functions. So there's a few different ones to choose from. On the next couple of slides, we'll look at probability of exceedance curves as a way to visualize aleatory variability. So this is a probability of exceedance curve for a specific scenario. It's a strike slip magnitude 8 at the rupture midpoint. The dashed line here is the Peterson 2011 elliptical model. And the brighter colors are our new fault displacement models. And they're probably noticing that they're clustered here in a much steeper curve, whereas the Peterson curve is quite a bit flatter out here. And this is a pattern that we see in a lot of the scenarios. The aleatory variability is smaller in the new models in most cases. There are some exceptions like smaller magnitudes or at the rupture endpoints, but generally we're seeing smaller aleatory variability. And a key feature and improvement of the aleatory variability modeling is that we have upper tail displacements that are in much better agreement with the empirical data. So if we look at the 99th percentile here, we see for example, in this very large earthquake, the Peterson model is kind of off the charts here. We're predicting more than 50 meters at the 99th percentile. This is well beyond any of our empirical observations of maximum displacement. And the new models, actually, with the improved aleatory variability modeling, are much more in line with our empirical observations. Same is true for reverse faulting, just to show the same plot, but for reverse. The Moss and Ross 2011 models in the black lines, they're not quite off the chart, but we do see the newer models have reduced the aleatory variability at the upper tails of the displacement. And so in summary, we have 4 new models from the FDHI project that provide fault displacement probability distributions. We have 3 models for strike slip faulting, 3 for reverse, and 2 for normal. It's really important to remember that there are different definitions of displacement used among the models. The components vary between net and vertical, and the participating ruptures can be just a single principal, the sum of the principal, or the aggregate. And Dr. Thompson will talk a little bit more about how we can think about these in a site-specific application in a couple more talks later today. The aleatory variability modeling, just like I just mentioned, we see upper tail displacements that are much more in line with our empirical observations of maximum displacement. And this gives us maybe a little more confidence, I think, that we can get reasonable displacements at longer return periods in the probabilistic analysis. And then finally, the final publications are coming soon. We're updating the technical report, which is published by UCLA and free to access, and the earthquake spectra paper is in review.
Great. Thank you, Alex. Appreciate that, as always. So we are going to have time for discussion. Let us move forward and then enter, please, all your comments in the chat box, or we are going to come back and verbally we can discuss. Next, Alex is going to talk about the computer codes for these new models. Alex developed both Python version as well as Excel version. Alex, you want to continue, please?
Yeah, for sure. Alrighty. So I will, in this short little talk here, I'm just going to focus on the Python code, but I think a lot of the ideas you can extrapolate into the Excel spreadsheet, and maybe we can talk about that more in the discussion at the end if people have questions. So as we've mentioned a few times, we have this Python package that implements the new models, as well as some of the earlier models. And we don't have time to go into all of the details, but there is package documentation available online that has more discussion and examples. So I'll just give you a quick overview right now. So what we essentially like a strict implementation of the models. It's not a probabilistic fault displacement hazard analysis engine. It's just a tool to compute the scenario displacements and exceedance probabilities. And we're focusing on the principal or sum of principal or aggregate models right now. Key feature of Python package that the calculation is verified. And so we do this with a set of independently computed results that are automatically compared with results computed by the Python package. And this automated testing framework spits up an error if the computations don't match, and we're not able to publish the package. So this kind of a robust approach to having verified calculations is I think a nice feature of this package. And I'll show you on the next slide that we can find some documentation on the package and some usage examples as well online. So there's a GitHub landing page. We'll paste this link in the chat in a moment here, but you can go to this GitHub page and find a link to the documentation. And the documentation will give you the information on the package API. The package is called FDHI, and you can install it with pip, which is the default package manager for Python. And it's an object-oriented API, which essentially means that we run a specific calculation for an instance of a specific model and its parameters. And that gives us our answer, our output. We have the 4 new fault displacement models that are coded up and available here, as well as the 3 earlier models that we mentioned in the previous talk. The parameters that you would use to initialize the model are probably what you would expect. Style of faulting, magnitude. XL is that X over L normalized position along the rupture length. Percentile is our aleatory quantile of interest for the deterministic assessment. And metric is what we use to describe the definition of displacement that's used in a model. So this can be aggregate or principal, depending on the model. And then version is the name of the model formulation. So for example, the Moss et al. 2024 model, they provide a D over AD and D over MD. We can specify that version here. All of these models have these parameters, but the metric and version will vary based on the model. And there are some models have some additional parameters as well that you can read about in the documentation. The calculations available to us, we can compute the displacement at a site at our given X over L location on the rupture. We can compute the average displacement in the earthquake magnitude. The models that provide maximum displacement, we can compute that. We can also compute the displacement profile, and we can calculate the probability of exceedance curve. This is a very quick example that you can find more in the documentation online, but what we'll do here, I'll just mention that I want to calculate a displacement profile. So this is a typical Python here, syntax here. We will import our library, which this library is called FDHI. And I want to make a plot of the profile, so I'll use matplotlib as my plotting library. And then I want to calculate the displacement profile for the new Cho et al. Model, which I want to look at a magnitude 8. So this is my model. These are my parameters, magnitude 8, the median displacement profile. And then the calculation I want to perform is displacement profile. That profile is going to return a default location array and the displacement amplitudes. And then I can, this is just the plotting syntax if you're familiar with matplotlib. That gives us our displacement profile for the specified parameters. The key thing to kind of notice here is that we're following the same example of our model name, our parameters, and the calculation we want to perform. So we have our package, I should say, then our model name, its parameters, and then the calculation is displacement profile in this case. Yeah, and there's many more examples in the notebook online, but they all kind of follow that same format of model, parameters, calculation. Oh, that's the end of the slides.
Perfect. I appreciate Alex. I know, Alex, you covered the Python. Do you want to say a few words about the Excel file and where is the Excel file also?
Yeah, it is. I'll put the link in the chat. You're right, since I have a minute here. This GitHub landing page, this is for the NHR Research Center at UCLA, and you'll find if you go to kind of the root of this page, you'll be able to find this Python package link here and the Excel file. The Excel file inspired by the NGA West Excel calculation sheet that Dr. made many years ago. And so I think if you're used to that, you'll hopefully kind of have an app for you enter your magnitude here and your location here, and you give model weight. It provides deterministic results in terms of you can specify your aleatory quantile, as well as probability of exceedance curves. And then it was initially actually developed as a probabilistic educational tool. So there's a little bit of a pseudo-probability element in there as well. It's not meant for probabilistic application, but the deterministic part of it is but what you would expect it to be usable, I think, in a lot of applications.
What's a legacy code? What are you referring to there?
Oh yeah, thanks. Let me get my pointer. So the first release of the code just had how do you call it, simple Python scripts, and that you would download and run locally as maybe individual scripts.
Still
But
Python.
Yeah. Still in Python, yeah. The difference here is that
we... Are you forcing everybody to learn Python? Is that the idea?
No, actually, that's why we moved it into a package, because when we use the package, you can just follow that cookbook of model name, parameters, calculation. The legacy code required a little more than a novice level Python, I think.
Professor, it is also the Excel file. It gives more or less the same information in a different format. And it's Excel. You just specify the magnitude and regular parameters, and it gives you the fault displacement. And in few seconds, Alex, if you're kind enough and you put in the chat the link for the Excel file also, you can download both Excel and Python, and they are 100% compatible in terms of numbers. They have been QA'd extensively by Alex and others. So if you don't want to use Python, that's perfectly all right. The Excel file will do almost the same. Very good. Again, we are going to have time for discussion. Let us move forward. Next, Steve Thompson is going to give you a couple of real-world examples. He is well-educated professional, practicing professional, and Steve is going to show us, suppose we have this example, more or less real-world example, how you're going to use the new models. Steve, welcome.
Yeah, thank you.
Perfect.
Okay. And the laser pointer for Dr. Idris. Excellent. Okay, as Yusuf mentioned, I will walk through a few examples of how we would use these new fault displacement models in practice. I want to acknowledge co-authors here, some close collaborators on these projects, foremost Arash Zandier and Nora Lewandowski. So what I want to cover, I have about 40 minutes. I have some initial topics to discuss, and then we'll get into a longer San Andreas example, an example of a lower slip rate reverse fault, and then, time permitting, I have some conclusion and recommendation slides to go through. So as a preface, the community that is using PFDHA is very small, and there's no broadly accepted best practices in PFDHA like there is for PSHA. So I just want to make sure that everybody understands some of the decisions I will talk about and some of the choices that I will talk about making. These reflect what we consider to be good or best practice, and but certainly alternative interpretations of how to use the models are very acceptable. So please take the attitudes and the approaches that I'm going to present here as reflecting kind of my own or LCI's practice, and not necessarily reflecting on the broader community. Also, it's really, I hope I can get across the idea that there are unique challenges to site-specific projects. Each site-specific project has different information available to inform it. There are different questions that are being asked by these projects. So there really is no one catch-all way to apply a PFDHA or even a deterministic analysis, as a lot of people online probably know. So that leads to the next bullet, incorporating PFDHA in engineering decision-making. It's really been a gradual process, and it will continue to be gradual. So for those people, we are noticing that there is increased desire, or there are more and more requests for PFDHA in scopes of work for lifelines or other important facilities. But exactly how to incorporate the results in your engineering decision-making, that's an ongoing process, and that requires a lot of careful discussion. So the examples today are going to focus on site-specific displacement hazard characterization. They're not going to focus on engineering solutions or risk calculations or anything related to that. We will be focusing on hazard. And the examples are being drawn from both past projects and current ongoing projects. And so I'm really kind of cobbling together these pseudo case studies. I'm not able to share any specific examples from start to end. So the other preface idea I want to get across is that when we're doing fault displacement hazard analysis, the PFDHA or the DFDHA part is just one part in the overall project. These projects are really multifaceted. As we commonly say, it's location, location, location. So step one in these projects is identifying where the fault rupture location hazard is, what's the uncertainty, and where the fault rupture is going to be. Other steps include what is the expected style of ground deformation at the site? What are the styles of ground deformation that these projects are really, these engineering facilities are really sensitive to? And only kind of in step 3 do we get to that displacement amount, where we consider owner seismic design criteria and we apply deterministic and probabilistic methods. And then there's some other steps as well, including kind of laying out scenarios for how that displacement that we calculate, how that would be manifest on the ground. And we usually come up with n-member slip distributions for design considerations, or again, oftentimes it's very much tailored to the specific projects and the specific, specific structures and specific questions. And then last, sometimes, not always, but the rate of displacement comes into play. On Monday, there was a question about afterslip. Typically in these projects, if we're working on faults where we think afterslip is an important component, we will document how that works in relation to rapid coseismic slip. Some engineering solutions are interested in the actual velocity of the displacement itself. So sometimes those other requirements are involved. All this, I should say, is from a paper by Givler et al. Presented at the ASCE Lifelines Conference. So first example, San Andreas Fault. I will draw a setting for everyone to picture from a project that's been ongoing for the LA Department of Water and Power for the Elizabeth Tunnel. This is the facility that gets the LA aqueduct water across the San Andreas Fault. You can see it's out here in the Antelope Valley, just beyond Palmdale. These slides, by the way, and some of these topics are summarized in a paper by Scott Linvall and others, again, for the ASCE Lifelines Conference. But zooming in on the Elizabeth Tunnel, this is a facility that crosses the San Andreas Fault at depth. The trace of the San Andreas in quaternary fault databases is fairly simplified. The cross-section of the Elizabeth Tunnel, it is on the order of 10 feet or almost 3 meters wide and about the same dimension and height. It was constructed in the early part of the 20th century, and it crosses the San Andreas about 90 meters or 300 feet below ground surface. And so there's the question that often comes up in these projects that involve tunneling is how do we apply these fault displacement models for surface that are based on surface fault rupture data? How do we apply them at tunnel depth? Other information, again, the tunnel otherwise is crossing through mostly crystalline rock. And like I said, just recently, the quaternary fault database shows a single strand at the crossing, making it look like a very straightforward problem. So site-specific projects often involve very detailed site studies. They commonly include geologic information, geophysical information, geotechnical information. For this particular project, where again, we're trying to characterize the fault at depth, not at the ground surface, the multidisciplinary approach included LiDAR and historic air photo analysis, transects of CPTs to get after some of the shallower units to understand areas of active faulting. There were both hollow stem auger core borings and a series of angled core borings that were continuously cored, and there were downhole geophysics as well. So this slide right here represents the summary of information that was collected from the site from this multidisciplinary activity. This type of mapping integrated fault scarps that were identified, offset alluvial stratigraphy, steps in the buried bedrock surface, all the way to trying to interpret the downhole geophysical data plus the continuous core. And so what we see here in blue, this is the map projection of the tunnel, and the final hazard zones are highlighted by both the purple and the red. And so we ended up with fairly broad hazard uncertainty zones at tunnel depth for this facility, but they're relatively well characterized. And we'll see where this comes in a moment. This now is a cross-section view. Here's Elizabeth Tunnel relative to the ground surface. You can see some of these shallower CPTs, these deeper angled borings. And one of the interpretations of the geophysical data and the core hole data is that there's coalescing of the fault strands at depth. And so what are multiple strands that are showing a stepping pattern at the surface, likely coalesce at least to some degree down to tunnel depth, and we can interpret one area of particular well-developed primary faulting and areas of damage around it and elsewhere along the tunnel where we interpret there to be secondary faults and shears present. One of the key logical steps that we make in this project is we tend to identify those primary fault zones and say these are the areas where we're expecting the principal displacement hazard to be. And if they're secondary faults and shears, we interpret those to be where distributed displacement is expected to be. Those are assumptions. We don't have any detailed paleoseismic data at the tunnel depth, obviously. So that's setting the stage for the type of information we can commonly get for these types of projects. Other site-specific projects don't nearly have the extent of that type of data, or the data may be much more ambiguous than they were for this particular project. So you get what you get, and you make the best of it. So now, turning our attention to the fault displacement analysis, we are focusing on the earthquake magnitude approach, as we've mentioned several times. For the probabilistic displacement hazard analysis, we need to develop a fault source characterization, or as the USGS has started to call them for the national hazard maps, an earthquake rupture forecast. We need to look at candidate rupture probability models, candidate fault displacement models for displacement exceedance, and we need to implement the full logic trees in some sort of hazard code. And then the outputs I'll show include mean and fractile hazard curves, some sensitivities. Deaggregation is possible in fault displacement hazard analysis as well. It's mostly right now just deaggregation by mean magnitude. For Peterson, that did have a log normal expression, we were able to deaggregate by epsilon as well. And we might get to more of that later. For a deterministic hazard analysis, we want to come up with earthquake scenarios, and those in our practice typically involve selecting a deterministic magnitude, and we have some sort of branch alternative weighting for different X over L or location along strike alternatives. I'll talk more about that in a moment. We also need candidate fault displacement models. These are simpler logic trees that we implement in a hazard code or some sort of Excel file. And from those, we develop displacement CDFs. So we'll walk through the PFDHA first. Here shows a type of characterization that we would use for a location on the San Andreas Fault. Up here, I should note, this is the formulation that Rui Chen shared on Monday. I borrowed this from her slides to help walk through the process. So this type of source characterization logic tree, this is an example that we have of an in-house model at LCI. Other practitioners are familiar with developing their own typically forward model approaches. USGS earthquake rupture forecast input, such as from USERF 3 or the more recent 2023 earthquake rupture forecast, that input can be used as well. But we need some sort of slip rate. We need some sort of description of the different rupture sources along the southern San Andreas that intersect our site of interest. This, I'll note, is a subset of the types of rupture sources that would be involved in a PSHA. And then we have uncertainty in our geometry and uncertainty in our magnitude and our magnitude recurrence model. So the next, okay, just continuing on, the next part of the logic tree we need to populate is the probability of surface rupture. And Lisa gave a brief talk about this on Wednesday, showing that there are basically, and we're aware that there are basically two types of model approaches. One is the more familiar empirical model or ergodic approach with Wells and Coppersmith 93. Also, their candidate models from Pizza et al., the 2023 study. And what Lisa and colleagues have introduced is an opportunity to do some source-specific numerical implementations. And so this shows some of the candidate models that we have. We selected for this project just the four models based on Lisa's new code. One of the important things to consider for this project is we have a magnitude area of interest for the San Andreas Fault that's at the very high magnitudes. I'm highlighting magnitude 7.3 and greater. For these, almost every empirical or numerical approach would show that the probability of surface rupture is about 1 or very close to 1. So this type of logic tree element can be very important if our characteristic or important magnitudes are at lower values, but at these very high values, this type of input doesn't tend to matter as much. The next rupture probability models are those two elements that get to the probability of surface fault rupture at your particular site of interest. And the question that constantly comes up for us in these site-specific projects is, would a probability less than 1 be justified given the site data that we have collected and interpreted? And so Rui mentioned that the P1 model tends to be considered a gap probability. What's the probability that the rupture will jump and not cross through the site? In this particular case, and in most projects where we map and we observe through-going active faults, we tend to think anticipating a gap at that location is under conservative. And then the other formulation, this P2, that deals with aleatory uncertainty and rupture location, we have to ask the question whether that aleatory variability is useful from project to project. First, this facility is a lifeline, so it's got to cross it somewhere. Also, we have this abundant site-specific data, and we believe that the site-specific observations of the faulting is just a different level of quality compared to the aleatory variability models that we have available, which are really based on the difference between pre-rupture fault mapping and then observations of the rupture later. Also, the issue of conservatism is an appropriate one as well. We ask a question, if we're unable or the client chooses not to collect any site-specific data, that would tend to favor the use of these types of models. But then we're basically, it's the opposite of penalizing ourselves for the lack of information. We would be tempted to use probabilities of less than 1 in cases where we don't have data. And that from a conservatism standpoint doesn't seem to sit well. Okay, candidate displacement models. This is what this conference is mostly about. We want to, in considering which models to use, which of these displacement definitions are most applicable, we want to think about the questions or the hypotheses that are relevant for a specific project. And so when we ask what definitions or what metrics are appropriate for hazard at tunnel depth that's around 90 meters below ground surface, well, we interpret there to be, and it's reasonable to expect that there's some degree of coalescing of those surface fault traces with depth. And so that right away suggests that the sum of principal or aggregate displacement models may be most appropriate to understand what sort of displacements we could expect on that principal fault zone. We also can ask questions such as, what's the deformation scenario that's most important to the operation of the facility, and what are the appropriate definitions or metrics to use for that? And here with the Elizabeth Tunnel, we're worried about a severing of the tunnel and a complete closing off of it, such that water or a pipe in the tunnel would be unable to convey any water. And so for that, we're really focused on not what the overall displacement is across the entire length, but really what could be localized in one particular spot. And so for that, it could be a principal metric, a sum of principal, or an aggregate, depending on the level of conservatism you want to consider. But again, slightly different questions could lead to slightly different decisions of which types of models you would implement. Okay, here is the fault displacement logic tree that that we have used. So, for example, we have separate, or first, I'll note that we do have separate logic trees based on the displacement definition in the metric. So we develop one logic tree and do one calculation for the sum of principal. We do a separate one for the aggregate. And then lastly, as a sensitivity, I'll show a run that was done on the Peterson model, which is just a single principal model. For all of these, the probability of surface rupture, we've selected a couple of different versions of the Memorella et al. Source-specific probability scale. We have the assumption that the probability of rupture at a site, given some surface rupture, is set at 0. And then for the sum of principal, we have equal weight for the Cho et al. And for the Labrantiadis and Abrahamson 23 models. For strike slip, for the aggregate, it's the same. We have the Kuhn et al. Strike slip model with half weight. Also for the aggregate, we have Labrantiadis and Abrahamson aggregate model for strike slip faulting with half weight. And then the Peterson elliptical model for the sensitivity case. Within model epistemic uncertainty is important. We haven't had time to implement that for this particular exercise. But as some of the model authors have demonstrated, that there are alternative models that would explore epistemic uncertainty within these model groups. And then the topic of additional epistemic uncertainty, obviously we haven't included that, but we'll touch on that at the end, that's one of the needs we think we've identified as an outcome of this project. Okay. So we have our source logic tree, we have our fault displacement logic trees. Now in looking at the hazard results, the software program that we use is an LCI code called TDIS-E. It is based on Norm Abrahamson's HAS platform. So those familiar with HAS 45, you can imagine a lot of the inputs and internal machines are quite similar. Activity rate is solved by moment balancing the accumulation rate with the moment release rate. Floating earthquakes are accommodated by defining different magnitude area and magnitude width relationships. This scheme right here shows how ruptures smaller than the full fault plane are floated both along strike and up and down dip. And then again, we have tools such as mean deaggregation, and then we can compute fractals using post-processing tools. One of the exciting things for fault displacement hazard analysis is we can check the hazard curve that we generate against a separately generated magnitude frequency or a comparably determined magnitude frequency distribution that's solved for a particular point along the fault. So we have some internal checking capabilities. Okay, finally, slide 17, and we're looking at our first mean hazard curves. So we have 3 different mean hazard curves reflecting the 3 different definitions of displacement. Our legacy sensitivity case is shown by the dashed gray line here. This is for the single principal case. And here we have in solid the sum of principal, and in the dashed dot pattern, the aggregate displacement metric. Consistent with one of the things that Greg mentioned on Wednesday for our very large magnitude type events, there is less of a difference between the aggregate and the sum principal. And so those are perhaps surprisingly close together. When we look at the percent change between the aggregate displacement definition and the sum of principal definition at 3 different annual frequency of exceedance levels at the 2 × 10⁻⁻3, the 1, and then something down here, 4 × 10⁻⁴, we can see that the percent change expresses the difference between the aggregate to the sum of principal. We have about a 9% increase down to about a 5% increase. These annual frequencies are equivalent to the roughly 10% in 50 years, 5% and 2% in 50 years. I will mention that these particular results are not for that Elizabeth Tunnel site. They're scaled versions of a calculation that we performed for a different location on the San Andreas. So I'm just scaling things to borrow them for our Elizabeth Tunnel location. Okay, fractile hazard curves. We'll look at the aggregate example. The sum of principal example is really similar. What we see with our hazard fractiles from the 95th percent, the 0.95 to the 0.05 fractiles, as well as the mean, we see that there's about a factor of 2 in hazard when we compare the 95 to the 0.05 for the displacement range of around 1 meter to around 10 meters. And so within a factor of 2 is really not too bad. And please remember that factor of 2 in a moment. So results are looking pretty good. One of the nice things about working on the San Andreas Fault is there's abundant other data that can be used to check the model. We have paleoseismic constraints. The McPhillips 2022 paper, which is an update of an analysis that Glenn Biazzi did for USERF 3, where they have looked at the different paleoseismic sites along the San Andreas and other major strike slip faults in California. And they've interpreted a mean long-term recurrence interval and also kind of 2.5 to 97.5 and 95% confidence interval of what the long-term mean recurrence interval is. So looking at the Fraser Mountain site, which is to the north, and the Pallet Creek site, which is to the south, we can come up with this paleoseismic constraint bar, and we can see that our fractile hazard curves are nicely nested within that type of constraint. So again, this is a wonderful advantage to working on the San Andreas. Hazard sensitivities. We'll focus on the hazard sensitivities of our fault displacement models. We have the sum of principal right here, where we can show that they're very similar shapes between the Cho et al. And the Labrantiadis and Abrahamson, really surprisingly close. The slight lower rate of ruptures in the Labrantiadis and Abrahamson model is due, we interpret, to that gap probability that's built into their approach. For the aggregate models, similarly, we have extremely similar shapes, very little difference between the Kuhn et al. And the Labrantiadis and Abrahamson. The hazard sensitivities that affect the rupture rates. We have the conditional probability of surface rupture that, again, is whether or not a given magnitude earthquake will rupture to the surface. As we saw earlier for this particular project, because we're focused on the larger magnitudes, there's very little uncertainty in hazard that's driven by uncertainty in our surface rupture models. Slip rate, consistently in PFDHA, uncertainty in slip rate drives our uncertainty in the rate of ruptures and in what kind of rates we're getting of non-zero displacements. And so in this particular hazard sensitivity, our low, preferred, and high slip rate really define a good part of those hazard fractiles, especially at the low displacement levels. Okay, now we'll switch to the DFDHA. And I'll run through these quickly given the time we have. The DFDHA logic trees that we've started to implement for fault displacement hazard. It's really nice that we can move away from the Wells and Coppersmith average displacement relations and trying to figure out how to adjust sigma to make it appropriate for a single location. What we can do now in the DFDHAs is we can again look for different target displacement metrics based on our question. We can consider that deterministic earthquake magnitude. I'll show examples for for a moment magnitude 8.1, which is below or just a tiny bit above the magnitude range of applicability that Alex just showed. Importantly, we encourage adding a logic tree for the X over L value. It's hard enough to call what the maximum earthquake is going to be. We are especially poor at predicting the endpoints of ruptures in our practice. And so having a hedge, including this as some epistemic uncertainty that we include in a DFDHA, we think is appropriate. For this exercise, we just have equal weights of various X over L values. And then we have the same fault displacement models that we did for the PFDHA. So here are the results for the DFDHA. Again, this is for a magnitude 8.1. Unlike the plots that Alex shared earlier, those were for a single X over L value. These, again, are averaging over different X over L values. The cumulative distribution function is shown against displacement right here. And for the sum of principal models, we have the Cho et al. Against the Labrantiadis and Abrahamson model. And we can see that at the 16th percentile, there's a bigger difference. We get closer at the 50th, and the 84th percentile, we're fairly close. But we're getting average displacements. The 50th percentile average between the two is about 3.8 meters. At an 84th percentile, we're at about 8 meters. This is a significant improvement over the earlier Peterson or the Wells and Coppersmith 84th percentile numbers. Let's see. This now is showing the DFDHA results across different displacement metrics, where we can say this is the average for the aggregate models, the average for the sum of principal models that we just showed, or we just viewed. And then here's that single principal Peterson et al. And so we can see for the 84th percentile aggregate, we're at about 9 meters, 8.1 for sum of principal compared to 14 meters using the Peterson et al. Last thing I'll mention before moving through the next set of results really quickly, we've talked about adjustments that are needed because of the fact that our net star displacement is less. It does not include the fault normal or the dip element, we think, in a large degree. In the case with strike slip faults where they're expected to be subvertical, net displacement is assumed to be roughly equivalent to the net star displacement. So these would be values we would encourage people to consider in a project. Okay, reverse example. We're looking at a shorter fault source. We're looking at a site that's near the end of a fault, and we're looking at a very different situation from the San Andreas, where here we have a very poorly mapped and characterized potentially active fault source, except in the local site area where we have much more abundant information. The source characterization is a similar type approach. I'll go through this really quickly. It's more important for this project, but not quite as important as we might expect given model choices that we made, and then I'll show. Again, this is the probability of rupture at a site, and we have to ask the question again, is a probability less than 1 justified? So we consider, is the gap probability justified? Aleatory variability, is that useful for a project? Again, in this case, we decided no and set it equal to 1. And now here we go back to these candidate fault displacement models. And again, we want to ask the questions for this particular project, which of these displacement metrics will be useful? Which types of questions will they answer? And so for this particular project, which involves a lifeline right along the surface of the facility, we are very concerned about localized principal displacement. But there are other questions related to the facility where the total displacement and the width of displacement is a concern. And so that suggests that both the principal and the aggregate displacement, both of those types of analyses can address different questions and give us useful information. Here's the logic tree that we implemented. Now we're using the Moss et al. Model with different within model epistemic formulations For the aggregate for reverse, we have the Kuhn et al. And Labrantiadis-Abrahamson models for reverse. And here's the comparison of the mean hazard curves, where we have quite a bit higher displacement for the aggregate and star displacement compared to the principal displacement that's a single principal strand and the vertical displacement measure. But importantly, here are the hazard fractiles, and this is very typical of what we get, where we see instead of that factor of 2 difference, we have about a factor of 15 to a factor of 135 in hazard from our NAG5 to our 5th fractile. And that's for kind of the displacement range of the 0.3 to 3 meters. And so the refinements that we're getting from the fault displacement model improvements are lost in some degree in the PFDHA because of our ignorance in the rate of ruptures that we expect on these very poorly characterized faults. Hazard sensitivities, a fairly similar story. Our hazard uncertainty typically is not driven by the fault displacement models. Conditional probability of surface rupture. If I had chosen a different logic tree, this would show up much bigger, but we made certain model decisions for conservatism here. But again, slip rate, this is the same story as before. Our ignorance and slip rate is our dominant contributor to our uncertainty in that PFDHA result. So our solution for that is to make sure we're cognizant that we're aware and communicating the hazard fractiles, but also when we turn to the deterministic analysis, we can focus on specific earthquake scenarios, such as the magnitude 6.6 earthquake that we selected as a maximum earthquake for this particular example. An X over L logic tree, we gave this logic tree an asymmetry in the weighting because we are close to the very end of this fault. But we're not willing to pick a single preferred value. And we have the same fault displacement model structure. So here are the type of deterministic results that we're getting. For the aggregate displacement models, it's surprising that there's such similarity between the Labrantiadis-Abrahamson and the Kuhn et al. Models for aggregate. Again, for reverse fault scenarios, adjustments are needed if we want net displacement. We need to, the recommendation is to take the net star displacement metric that they're able to solve for and divide it by the sign of the dip, and the dip would be site-specific and subject to site-specific uncertainty. Deterministic results for those principal displacement exceedance models. Here we're looking at just 2 of the more conservative Moss et al. Models, and we see their results are very similar. Adjustments are needed for this displacement metric. If we're after net displacement, we need to divide the vertical, that's a typo there. The vertical displacement amount that's computed, we need to divide it by the sign of both the dip and the sign of the rake. And here, this will be my last slide. Here, we're looking at a comparison between the single principal vertical model that's shown in the solid line versus the dashed dot line of the aggregate model. And what we're showing here are the values using the displacement measure, and then in brackets showing that computed net displacement using a dip of 45 and a rake angle of 60 degrees. And what we can see is that at 16th, 50th, and 84th percentile, the aggregate tends to be around a little less than 10% greater to about 20% to about 26% or so greater at the 84th percentile. So again, this is useful information we can bring back to a project when we talk about engineering consequences. So I have a set of conclusions and recommendations, but Yusuf, why don't
if you keep going, these are very important.
Okay, great. Yeah. So conclusions and recommendations. So as Alex has mentioned, the new fault displacement models, as well as some new rupture probability models, they're ready for use. They're also ready for further testing by the practicing community. We have appreciable improvements in these models for mean hazard, especially at the lower exceedances, or higher exceedances, I'm sorry. And we need to be aware of the different displacement metrics, as we've said numerous times. These are potentially very useful for addressing different questions about the hazard for different site-specific projects, but the hazard does need to be run separately for each type, and the results can be compared after the fact. We shouldn't be mixing these models within the same logic tree and the same calculation. Other points, I'd like to make sure everybody considers different levels of confidence in PFDHA results when we compare providing these results for well-studied high slip rate faults, such as the San Andreas or Jacinto or Hayward, perhaps. Very different story where we're looking at poorly studied low slip rate faults where we're really swimming in ignorance about the source characterization. In either case, the new fault displacement models are very well suited for deterministic hazard analysis. And the PFDHA for poorly studied low slip rate faults, it still can really add value to a project, but it requires some special attention and special communication with project people involved in projects to understand how it best can be used for engineering decision-making. That's really been a lesson we've learned many times over in the last several years. Finally, some recommendations for additional work, some things that our group, the FDHI group, has talked about. We need a project for PFDHA hazard code verification. We need guidance from within our model teams for how to add additional epistemic uncertainty to our models. A lot of these models, you can see, had extremely similar predictions. For distributed displacement models, that's a big need that the FDHI group is aware of and will be working on next. Those distributed displacement models need to focus both on the exceedance equations and those rupture probability parts. So Francesco mentioned this on Wednesday, one of the new distributed displacement models. There are some other wish list terms. We need to understand better statistics for the width of expected faulting. We need to continue to work on pre-rupture fault mapping and understand rupture location uncertainties. And then the last one really is we need as a community to develop better guidance for engineering decision-making, how to work through PFDHA results, again, can be very different from PSHA. And that's it. Thank you.
Perfect, Steve. I appreciate that. Very, very interesting presentation. So let's have 5 minutes break, and then we'll come back and we will have several minutes of the question, answers, and discussions. Let's come back at 11:15 Pacific times. 4 minutes break, 11:15. We'll come back in 4 minutes. Thank you, thank you, thank you. All right, let's unmute ourselves, and we have several minutes for questions and discussions. Already there are a couple of questions for Steve. Steve, did you read it, or Alex or Rob, can you read it for Steve? There are 2 questions by Brian.
Yeah, and actually, Brian Swanson, if you want, you can do the little React hand raise, and I can spotlight you and you can ask yourself, or we can, if you don't have a good internet connection, we can read your questions. They're very clear. I don't see any spotlighting.
You want to talk about it, or?
So Brian, yeah, Brian, if you want to join and chime in, that's great. Otherwise, yeah, this is 2 excellent, very detailed questions. I will say that I've had a lot of fun talking to Brian. He's one of the geologists, paleoseismologists, who's been thinking very deeply about PFDHA for a while, and conversations with him have always been interesting and great. So his question is related to slip rates. And And a lot of the statement is a lot of the slip rates assigned to faults are based on paleoseismic investigations. And so a given site will only record rupture displacements that reach the site and the portions of the displacement that reach the site during a given rupture event. And so if the slip rate incorporated into a PFDHA is already limited to those displacements, should these probability factors basically be factored into the analysis a second time? Basically, should we be looping back over ourselves? So that's a great question, and I think on a fault-specific basis, that would be an excellent thing to discuss. I think I'll challenge a little bit the idea that most of the slip rate information we get is limited to just what we interpret from paleoseismic trench investigations at specific locations. Oftentimes, the slip rates that we have for our faults and the slip rate uncertainty, it incorporates uncertainty in geodetic modeling, it incorporates uncertainty in geomorphic offset measures that span a much broader area surrounding the fault zone. So a lot of the slip rates that have been going into the national hazard maps or that we use for our other projects aren't necessarily slip rates determined by very narrow aperture location-specific views. Would you agree with that, Brian? I mean, is that a...
Yeah, and that's what I was trying to differentiate. If your data is based on a site-specific investigation, I know they're not all entirely based on that, but if that's the case, then
yeah. So that's absolutely something to be mindful of. And I guess the other thing I'd say is that in most actual case studies where we do rely on trench information to get a slip rate, maybe it's a fault that's been identified as active, but it doesn't have a well-characterized slip rate, our ignorance in that slip rate that we derive from the limited paleoseismic data would swamp this type of concern that you have. And so if you think about the typical investigation, we would be able to recover 1 or 2 paleo slip events. We'd have dating uncertainties. We'd have to incorporate additional uncertainties related to in any number of things. So in our experience, our uncertainty in slip rates is significantly expanded over our uncertainty of slip rates that we would get from a single trench observation. So I like this point that you bring up, but I don't share it as one of the top concerns that we have for most of our projects, if that's fair. And then I really appreciate the second comment. Should displacement exceedance values obtained from a hazard curve for a given site and for a design return period of interest generated with the earthquake method be reconcilable with the rupture displacement history revealed in a paleoseismic investigation? So right there, the gold standard with PFDHA or with any fault displacement hazard analysis should be using the direct approach. It should be based on paleoseismic information for past slips collected at or close to your site of interest. The main what's preventing the displacement approach from being implemented more frequently is that there are very few situations that can really accurately preserve single event displacements. We don't have our choice of paleoseismic sites when we're dealing with a lifeline crossing that's in a certain urban corridor or a certain dam that's been constructed in bedrock situations. And so in places, in the few studies where we've been able to have extensive trench observations, we've used the displacement approach that's explained by Youngs et al. We need to, so we can really leverage those paleoseismic determined displacements. And then our aleatory variability is the next question that we need to add to those hazard assessments. And in that, the approaches to solving that term are a whole nother talk. But to try to answer your question as best as possible, if there are good site-specific data on single slip events, single per event displacements, that information should be used to drive the fault displacement hazard, not the earthquake approach, full stop.
Yeah, I guess going from there, my thought is what I've seem to be seeing is that if you try to pick a set of displacements that will give you your slip rate, if you don't have all that information, you only have limited information. But if you look at any combination of events that will get you to your slip rate over a given amount of time, it seems like sometimes that requires higher displacements than the PFDHA earthquake model generates. Like, there doesn't seem to be a compatibility there. Like, you have to have larger displacements to get to the slip rate, whatever they are, even if you don't know what they are. Like, to get to the slip rate, you need more than the PFDHA model seems to generate, at least at shorter return periods.
So yeah, we've had some discussions about ways to interpret the hazard curve, and there are additional discussions we should have about how to deconstruct a hazard curve. And from a hazard curve, you can construct a displacement PDF, so you can observe the actual slips that the model is considering to recover the slip rate. And that's the type of more useful information, I think, for these types of discussions. So, yeah.
Thank you. Thank you for the
Very good.
insights.
Yeah,
Very
thank you.
good. Thank you. All right. One more question for Steve. Steve, either you read it or Anna, you want to say it yourself, or Alex?
Yes, let's see. So Anna had a more general question. You're welcome to ask, Anna. If you do the raise your hand button, I can find you.
You piqued my curiosity, Steve. And if you're able, I understand you work for private clients and maybe you can't share everything, but you mentioned, bringing PFDHA into engineering practice and some of the lessons learned. My curiosity was piqued, and I wondered if you could say more about that.
Yeah. Let's see. We've given talks at SSA, and I think Norm gave a talk at a Cal Engineering conference. One of the big issues that, one of the concepts is how we appropriately use the fractals. And the fractals are an expression of our ignorance, our lack of knowledge about the hazard at a particular location. And we're commonly driven in engineering decision-making to rely on the mean hazard curve in PSHA, and for very good reason. It's well-established standard practice. And the idea of designing for levels that are safe enough for the given project or for the given opportunity, those I think have been it's well-trodden ground in PSHA. In PFDHA, where the range of uncertainty in our fractals is significantly greater, and it's driven in large part about your one particular fault's source characterization and rate of ruptures, that just requires a different conversation. So you need to discuss with engineers what those higher fractals mean, what are opportunities, if any, to reduce the hazard uncertainty through more work, or if more work is not possible due to whatever constraints, how do you try to use those hazard fractals in your decision making? And those are difficult decisions because there's no standard practice. Which fractile do you use? The 95th? Do you use the 84th? Do you use some other fractile? And so that's one topic. The other topic is that the common return periods, or the common exceedance probabilities that have been used for PSHA, the inclination is to use those same hazard levels for PFDHA. And if it's the 975 or 2475 or the like, based, with the decision based on the importance of the structure, that's fine if and things work out if you're the San Andreas fault, if you're the Hayward fault, if you're the San Jacinto fault. The types of displacements that we get at those sort of probability levels they result in displacements that are at or larger than the expected mean displacement from different scenarios that you envision. And so it passes that litmus test of this is safe enough. I'm using my PFDHA to guide me towards a displacement that's greater than my average expected displacement given these large scenario earthquakes. When we're dealing with our much lower slip rate faults, we commonly find that our 975 or 2475 levels, we're looking at either these hazard curves lie entirely below those hazard levels, or we're at the upper part, that shallow, gently dipping part of the curve. The displacements that we commonly get from the PFDHA are what we call negative epsilon results, or given scenario earthquakes. These are much lower than the average expected earthquake. So it would be equivalent to doing a deterministic hazard analysis and deciding to design for the -1 sigma, or design, 16th percentile, or designing for the 5th percentile. We've had those situations. And so that again becomes a difficult conversation, or a complicated conversation to have with a project of what exactly does that mean for your structure. Does that make sense? I'll stop there.
Yes, it sounds like a familiar conundrum. Yeah. Thanks.
I wanted to add what Steve said, that 2,475 or 975 years return periods that we use it on daily basis, coming from the building industry with lots of experience about the damage of the buildings, different things, and so on. We have to re-examine these numbers for, say, pipelines, lifelines, and so on. As Steve said, that is really something that as a community we should do that, rather than just copying what has been used for ground shaking and for building industry. Great. Ken has another question. Ken, Alice, can you unmute Ken? Ken Hodnett?
Yeah, I don't know if you can hear me.
Yeah.
Yes.
Okay. Yeah, I guess I'm realizing maybe this was not such a good question I'm asking in the chat, but what I'm getting at is, so somewhere the information about the past earthquake history, maybe that's coming through in the probabilities that you're getting, say, from USURF3. But, it seems to me like when we think about the Coachella section of the San Andreas Fault, for example, there's possibility that the slip in this next event down there might be larger than the average slip in past events because it's been longer than the average recurrence interval. Is that something that can be accommodated where you do have such additional constraints?
Yeah, good question. So what we would typically do in a PFDHA is we would treat that in the source characterization with more of a time-dependent analysis. So that would increase the annual probability of there being ruptures, which, if we're focused on a different hazard level, or if we're doing a risk analysis and we want to look at different points on the logic tree, that will change the hazard. So that is an advancement of the clock. That's an advancement of time for the next rupture, the probability for the next rupture to occur, not necessarily for the amount of displacement that's expected from that event. That's storing of strain energy that you interpret could be released at once in the next event. And I know that actual topic, when we think about the papers that Ray Weldon and colleagues have written about the Wrightwood observations, or basically some hypotheses about that next event and what amount it would be, there's really nothing in these current models to explicitly put in to tune, other than something that you would just decide on for a specific project.
Okay, thanks.
Yeah.
Very good. More questions and comments for everyone, for Steve, for Alex, regarding computer codes, regarding comparisons of the fault displacement models. Any questions and comments? We have 3-4 minutes.
I guess I raised my hand, but you
Oh.
can see.
Oh, we missed it.
Sorry, but I do have a couple of questions, and then I have a more generalized question. These are to Dr. Thompson, the first two questions. One is when Alex was presenting the comparisons among the various models, she showed a huge difference for any displacement at any given return period, or the return periods for a specific displacement. Whereas when you compared your results for San Andreas, certainly it was almost practically the same. Is that because of San Andreas, or what is the
Yeah.
variations here?
Alex, why don't you go ahead?
Yeah, I have the probability of exceedance curves that we showed for the magnitude 8 strike slip event, and the new models were actually very tight. We can look at that slide again, but they were almost right on top of each other, which is, I think, pretty consistent with what Steve showed. And then the second set of curves were for a reverse magnitude 8, and those were a little more spread out. I'm not sure what magnitude you were looking at in your. I don't remember your deterministic reverse. It was slower than 8, though. 6.8 or something. Yeah.
6,
yeah. So I don't know that they're incompatible, but they might have just.
But if you're in Los Angeles, you're worrying about a lot more than just the San Andreas fault.
Oh, yes, yeah.
Yeah.
And
but
the second, I guess that's the answer to that question. But the second question was about just the comparison between the mean and the median for the when you showed the fractals. When you had a tight fractal distribution, they were practically identical. Even when you had a huge difference between the 5 and the 95, the mean and the median were not that different.
Yeah.
But when we first started looking at fractals some 50, 60 years ago for nuclear plants, we always found that the mean was about close to the 80 percentile because of the high uncertainty. And that's why actually we insisted on using the mean for the design rather than the median, or the expected value. So is there something going on there that you have huge difference among the fractals, and yet the mean and the median is almost the same?
Yeah.
That sounds a little surprising.
No, that was surprising to us too, and we did some checking at even lower exceedances. There is more of a separation, and we have a lot of projects where we do have the expected behavior, whereas we get farther down farther down the hazard curve, we get a drift of our mean hazard towards the 84th percentile. So the pattern that you've come to expect, we do see in a lot of cases. In these particular cases, we didn't, and part of that, I think, was where I clipped the plots. We didn't get to see them even farther down the hazard curve at other levels. So, but
should I expect that all the time, or should I get back to normal?
I think it's a case-by-case question, and as a reviewer, that is certainly an important thing to point out.
I do review quite a few projects. I have one comment and one more question. The comment is when the point that I think that Dr. Bisogna was making about we have to look at the return period that we look for fault displacement differently from what we've looked at ground motions. It's really more in terms of looking at equal risk. If you look at equal risk for faulting compared to equal risk for ground motions, you need a higher return period for the fault displacement. So if we keep that in mind as we go forward, I think we'll get the two to sort of eventually meet, so to speak. But the last question I have is quite different from nothing to do with the presentations. one of the issues that always comes up on a lot of dam sites is there are features that are not non-seismogenic, but they could displace. And therefore, any displacement that might occur would be caused by a major fault some distance away moving. Has that been considered in this project, in this huge effort that you guys going through, or do you have the data to shed any light on that? This is an extremely important issue that comes up on many dam projects. So, anything you can enlighten us with?
Yeah, Dr. Itters, all three of us are trying to race to be the first one to answer that question.
Go for it, Steve.
I will mute myself after this. That's the last last question I have.
Yeah, that's a topic that we address very often. It addresses distributed displacement hazard instead of principal displacement hazard. This first part of the FDHI project is focused on fault.
That's really not the issue. I'm talking about faults being 5, 6, 10, even 20 kilometers away from a major fault.
Yes. Okay.
Triggered.
So it's not a distributed issue. It's a is more of a secondary or sympathetic movement.
So that
I'm just asking if the data are available within your the flat files you've created or the data you've collected. Maybe that's a question more to Dr. Bezonia and to Alex.
Alex.
Yeah, so the trigger in the parlance, I know Peterson called it triggered. Maybe that goes back to the Yucca Mountain days. Those triggered displacements that are on other faults that are capable of making their own earthquakes and happen to be triggered by an earthquake, 10, 20, even 50 kilometers away. We don't have those triggered displacements in the database. We focused on the principal and distributed type of displacements. The most egregious example that always stands out in my mind of triggered displacements was from the El Mayor Cucapá earthquake, that triggered displacements on faults 80 kilometers away. That was the first case we ran into. Oh my gosh, does it make sense to include this in the database? And the short answer is it didn't. That's a different phenomenon that we're not trying to model. We're not targeting with these set of models.
I'm talking more about non-seismogenic, actually. Features that are non-seismogenic, but large enough that might produce a foot, 2 feet, 3 feet even, possibly. You can see that in the, but they're called sympathetic, actually. I think that's the term that's used, sympathetic movement on a feature it will never move by itself. It's never seismogenic.
Yes. So.
And that exists on many dams, especially in California.
Yeah. So when it's, I'll use the phrase near field very loosely. When it's near field and recorded in the original data sets, we have captured that and we call it distributed faulting. And
it could be far enough that it cannot be part of it. But anyway. So
yes. The data are incomplete. And I don't, it's a little bit of a data problem and a little bit of a forward modeling problem. Yeah. I do want to mention, FIA has mentioned that in the SURE database we heard about on Monday, some of these displacements, well, the rank 3 displacements, they have some triggered displacements and some of the kind of the random fractures of, if you will, broken out a little more in the SURE database.
It came up on Calaveras Dam, which is about 3 or 4 kilometers away from the Calaveras Fault, but it has no seismogenic features crossing the dam. And
okay, yeah.
But anyway, so that's
all right. Thanks. We'll think about that.
It's like aftershocks and main shocks in the
you have to collect the data. Just for a few seconds, I don't want to cut. Andrew asked about the fragility.
Yes.
Andrew, fragility is the biggest elephant in the room and is very labor intensive. As I mentioned on Monday, for natural gas transmission pipelines, not the pipelines that coming to your home and to our home. We have developed a very, very comprehensive database of fragilities. We have another proposal which is being reviewed for water pipeline, transmission pipeline. But as Professor Edris day one mentioned, these are structure specific. So we have to vary the size of the pipeline, the pressure in size, depth of the soil, lots of things. As soon as we organize ourselves and we have reached to a level that we can share the fragilities, obviously we are going to share. We need to move.
May I make a comment on that?
Sure.
I think it would be really very helpful to have a coherent methodology that's repeatable. It's somewhat fragmented the way I see it. There's a lot of work has gone on buildings and such, but hardly anything related to this type of situation where faulting is important.
You're absolutely.
So maybe that effort, the UCLA can take on that kind of effort. That'd be very, very valuable, I think, for the entire profession.
You're absolutely correct. And as I mentioned the other day, we are behind. Again, for building industry, they have been working on this for decades. We are behind, but it's definitely needed. Unfortunately, it's labor intensive, but we should do it in a coherent way. So we need to move forward. There is one important but short presentation by Steve Thompson again. In the middle of the Fault Displacement Hazard Initiative, the idea came in with another project funded by California Energy Commission. What we developed similar to the ground motion hazard map, we developed fault displacement hazard map, at least for the state of California. It's the first step. It's not the final step. And Steve is going to give you where we are. Steve, welcome again.
Okay. Okay. Someone scream if you can't see my screen. So I will, in the interest of time, I'll try to keep this very short. A lot of people have heard different versions of this talk before.
Yeah, Steve, you might not be sharing. Are you intending to?
Yes.
Zoom strikes again.
Let's see.
That's looking
good.
Better? And
Presentation. Yeah.
Perfect. Yep, I bet that's what you're going for.
Yeah. I'm sorry about that. So I'll try to keep this very brief. I have more slides than I have time to talk. This is a version of a presentation that we gave in May down in New Zealand. So if Tim or any other New Zealand colleagues are online, you can see some familiar slides and topics. I'll acknowledge the collaborators on this project, Arash and Ality at LCI. Danielle Madugo played a big role in some of the early classification. She was with UCLA at the time. Now she's with CGS. And then, of course, Yusuf for continuing to inspire us down this road. This is a project to put together some sort of preliminary probabilistic fault displacement hazard map of California. And so the subtitle is, we're hoping for a useful product despite an imperfect approach. And we'll go through the motivation and some of the inputs, et cetera. So the motivation is we want to introduce PFDHA to a broader community, and we want to highlight the new fault displacement models under FDHI. Also, a lot of people are interested in some sort of system level tool for understanding fault displacement hazard and risk. So owners of big distributed infrastructure or people planning long new lifelines are looking for some sort of way to do hazard screening. And a third motivation is to stimulate some discussion about fault displacement hazard mapping and mitigation. So the big things that this map is not, it's not a tool for communities to do any kind of zoning or city planning. It absolutely is not a tool to be used for engineering design, and by no means is it a replacement for site-specific work. The overall approach, this project was started prior to the most recent national hazard maps and the most recent earthquake rupture forecast. So we used the USRF3 sources, and one of the valuable elements that USRF3 developed was also the set of polygons surrounding the different USRF3 sources. And so we're using that as our earthquake engine for our magnitudes and rates and locations. And then for the more specific location of where the rupture would occur at the surface, we're using the USGS CGS quaternary fault and fold database. The intersection of those two, which I'll explain in the next slide, is to produce a set of, basically a set of rupture traces that have associated with them some sort of displacement hazard curve. We're not able to include displacement hazard for every single quaternary fault trace in the CGS database. We can only provide hazard curves for those traces that fall close to one of our USRF3 sources. So hopefully we're getting the major ones. A couple of slides quickly about their approach. We're using the USRF3 rupture sources, again, represented by these red lines in this image. And we're using the fault polygons down to the resolution that the USRF3 project allows. And so the smallest elements in the USRF3 model are these tiles or subsections. And our resolution is pretty much bound by these USRF3 subsections. And for each subsection, there are attributes that you can extract about the fault geometry, the rake, etc. And then the solution files give us information about the ruptures that each subsection is involved in, along with their magnitude and their rate. Again, we need more precise locations on the ground of where the surface fault rupture is likely to occur. So for those, we use the Q-fault database. And so again, Q-faults that lie outside of these polygons, we just weren't able to incorporate them. So they are not considered with a few minor exceptions. These quaternary fault traces, they're linked to those USRF3 subsections or tiles. So the attributes for the source characterization are joined with specific Q-fault traces. And then one of the major steps that is placing us a little bit at risk is we need to do a classification scheme for each quaternary fault trace to understand whether those fault traces are capable of full principal displacement hazard or maybe some sort of secondary or distributed displacement hazard. So the quaternary fault, aside from the quaternary fault location and the precision and the location of those traces, another major sort of task that we're undergoing is how do we classify each quaternary fault trace as one that clearly seems to be a potential for hosting principal displacement rupture versus other strands in the Q-fault database that don't have that kind of continuity or don't have that sort of geomorphic association, where we're trying to figure out what kind of useful classification system can separate out the different traces into a way, again, that can be useful for trying to characterize hazard at a statewide level. So at first, we came up with two different classes of secondary displacement. We have a decision tree that Danielle and Ality developed to do this classification across the state. And some examples of the classification scheme. Here we have a reach along the Big Bend of the San Andreas, where in red, we have what's tagged as the principal trace. This more anastomosing pattern in purple is the secondary class 1. And then these bluer traces that are farther away from the fault source seem to be kind of maybe reflecting more the past history of the San Andreas and bedrock geology, these are inferred to be secondary class 2. Another example along the Green Valley Fault in the Bay Area, Northern California, we have cases where we have long continuous strands that we can interpret as potentially hosting principal ruptures, ones that are close to it, that branch from it, that are interpreted to be secondary class 2. And then we have a whole host of more distant fault traces that we assign to the secondary class 3, including some sources such as the Cordelia Fault, which in our local seismic source models are interpreted to be independent seismic sources. So these aren't sources of earthquakes in the statewide models, such as USERF3 or the 2023 earthquake rupture forecast. They are considered to be independent seismic sources by others. The only way to fit them into the classification is to treat them as some sort of secondary rupture. Rupture location uncertainty, we have struggled with an appropriate balance between how wide a buffer should be for uncertainty versus wanting to give some sort of sense of precision to a fault displacement hazard map. That's all I'll say right there. Oh, I'll also say that for the first attempt, we ended up merging principal and the first class 2 secondary together. The logic tree that we've used is based on combining the new fault displacement models with various weights. We went ahead and did what we just spent a few days telling you not to do, which is we mixed different displacement metrics and combined them in a logic tree for this demonstration project, at least for the first event. We also are not using fault displacement models for distributed displacement, so we're handling those secondary displacements by basically taking probabilities of rupture less than 1 and also scaling down the displacement exceedance. This is the type of result that we're getting, where we have metrics like, for example, we'll be able to show maps of fault displacement mean return periods for greater than or equal to 1 foot displacement, where the different colors represent different return periods. We are going to have metadata associated with this, where you can see the attributes of different sections, points on a hazard curve, and then displacements at various kind of commonly viewed return periods. So several concerns about what should be included or not included with this project. It's going to be an imperfect approach when we look at different fault trace work that hasn't been vetted or incorporated in the quaternary fault database. We already know that there are going to be some well-mapped fault traces that are outside of these buffer zones. We're trying to figure out how to guard against misuse of this type of model, knowing that these types of outcomes are going to be present. So our plans, this project is moving slowly. We've been focused on getting our new fault displacement models published, but we'll be returning to this. Our plan is to do workshopping with CGS, with USGS, so different stakeholders understand what we're trying to do and can provide feedback. There's concerns about the ownership of this project going forward and who is kind of responsible for maintaining it or adjusting it. And then most importantly, how do we keep this as a useful tool for the right applications, but we want to safeguard it against inappropriate use. And so I'll end there. Thank you.
Perfect. Thank you. Thank you. Thank you. Again, I remember decades ago when first time USGS started with probabilistic seismic hazard maps. Obviously, there were discussions and so on. We are at that level, that stage. So we start, obviously, the start is not the perfect start, but over time, we are going to improve it. Thank you, Steve. I appreciate that. We have literally 5 minutes or less. Anything anyone wants to share, any question, any feedback, any comments? If you feel that the time is short, again, it's not the end of the world. You can share with us after the workshop about your feedback, your questions, your comments, and so on. anything that you want to share with us in the next 3-4 minutes?
Can I express my thanks for everybody and the great job all the speakers have done? I think this is a very valuable exercise. Thank you, Yusuf, for organizing that.
I appreciate Professor Regis, really. Thank you, thank you. Again, this is a community-based project. You will see the papers are coming up, the reports are coming up, the data and models are coming up. You're going to use the models, you're going to use the codes and so on. Please give us feedback. Really, the key of such a community-based project is for you to use their data and models. This is not just abstract or publishing a paper. So please give us feedback. If you find typos, errors, anything, we love to hear from. Anything else from anyone?
Yeah, this is Gordon Scythe. I had a question for Steve on this last presentation. You have this class, you call them class 2 secondary faults, right?
Yeah.
You have a certain, do you have a threshold of when those faults become principal faults or
Yes.
primary faults?
You mean from a classification sense or in?
Yeah, well, because you said that they can be considered primary sources, right? Or they can have their own earthquakes, right?
Okay, so
do they at some point become primary faults?
Yeah. Oh, okay. So I may have introduced some confusion. So the example there was for the Cordelia fault. We have other examples, for example, the Pleasanton fault. So in other hazard projects, those are considered capable of generating their own earthquakes. The national, we're relying to make this a tractable statewide project. We can't be adding additional sources. We need to rely on a existing statewide source model. And so the obvious ones to use are the community models like USERF3 or the 2023 ERF. So the question is, what do we do about those other faults that we understand separately are capable of their own earthquakes? And our solution for that is we recognize that those are lower slip rate faults. Their earthquake magnitudes and displacements are likely to be lower. All of those are handled indirectly by scaling the rate of events and by scaling the displacement amounts. And that's what we do to that class 2. So that's how we try to shoehorn it in. Okay. Imperfect, but it's something we've.
Yeah. So mostly it's by slip rate then. Is that true?
It's not a slip rate because we don't have control over slip rate, but it is a penalty on the probability of ruptures. So it's comparable to slip rate adjustment.
Okay. Yeah. Okay.
Very good. Appreciate that. As previous sessions of the workshop, Alex is gonna share with you the recording of this session as well as PDF of the presentations for today. Before we close, I really want to thank all the speakers, all the individuals and organizations that contributed to this large project over the last 4 or 5 years. We couldn't do it without really the teamwork that we have. Thank you very much, everyone, especially one person I really like to thank, Alex. Alex has been the force behind the project, organizing and putting lots of efforts. Thank you, everyone. We will be in touch. Thank you, thank you, thank you.
Right. Alex, Yusuf, thank you guys.
Yes, thanks so much, everyone.